Greetings and welcome to the AATRN Topological Complexity Seminar. Our speaker today is Kevin Schreve from LSU, who will tell us about right-angled subgroups of graph braid groups.
Okay, thanks, Dan. Thanks to everyone for coming. Thanks for the invitation to speak. So I think Dan put me in a bit of a pickle for this talk because I have a recent result with Kasha on what I'm going to talk about. It has applications to topological complexity. And I'm, speaking at a place where everyone knows much, much more about topological complexity than me. Okay, this is not my usual thing. So I'm going to do a standard trick and talk about our motivation or what kind of got us started thinking about this project. And then I will get to the parts where we can say something about this topological complexity graph braid groups. Okay. So I'm going to, so this is starting, let me just start a ways back. Okay, this is what Kash and I started thinking about this project. So this was, and I should say, just stop me at any point for questions. So it'll probably help me. So this was a theorem of Crisp and Paris, which kind of is still colloquially referred to as the Tits conjecture. Okay, though when I called it the Tits conjecture and Paris was in the audience, he wasn't all too happy. So it's a theorem of Crisp and Paris from about 2001. Let me say what it is. Okay. So you take any Artin group, and I will, describe what these are, give you a presentation for them. Okay. Then the theorem is the squares of the standard generators generate, well, another Artin group, but this is now a right-angled Artin group, which people are probably more familiar with, I think, at least in my circles. So if you want to think of kind of the standard example of an Artin group is a braid group, and this theorem is already kind of interesting in the case of a braid group. And it's kind of notable in that it's one of the few theorems that are known for all Artin groups. These are generally kind of very mysterious classes, not, there's kind of very few general theorems, and this is one of them. Oh, maybe I should just say this is, whenever I write RAG, that means right-angled Artin group for now on. Okay. So let me kind of explain the theorem with an example. Okay. So let me give gamma is going to be a labeled graph. Okay. So let me just put this here. So I have vertices labeled by S, T, and U. And then I label the edges with integers typically greater than or equal to 2. It doesn't have to be a complete graph, so you can always, if there's no edges, that's fine. Okay, in this example it is. Okay, so this is gamma, and then there's an associated Artin group to gamma, which is you have the generators correspond to the vertices of your graph. Okay, and then you put in relations corresponding to the edges, and the labels dictate exactly what the relations are. Okay, so if you see, let me just go through this. So here I see a 2 between an S and a T. 2s in the kind of labeled graph, correspond to commuting relations. So S and T commute in this picture. T and U, there's a 3 there, so I write kind of the standard braid relation. TUT is equal to UTU. And I do the same for S and U. Okay, so FUS is equal to USU. Is that okay? And then, okay, so in general, what you do is if you see S and T, and there's a label M, okay, well, again, S and T were generators, and now they satisfy the relation where you go S, T, S, blah, 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 m times is equal to TST m times. Okay, so this, I guess you could call it a generalized braid relation. Okay, so this is the general picture. You take any labeled graph, you get this presentation, it gives you a group, and in some cases, it turns out to be groups that you know. So in this case, let me just say this is, in this case, A gamma is the braid group on 4 strands. Okay, braid group on 4 strands. Okay, so that's what kind of an Artin group is. And now let me say what their theorem should say. Okay, so now we're looking at the squares of the standard generators. Okay, let me try to move this so my handwriting can, well, it's not going to improve, but I'll attempt. Okay, so what should their theorem say? Well, now we're going to make kind of another graph, looking at S squared and T squared and U squared. Okay, and now what should the relations be between the squares of these elements? Well, S and T commute, which means that S squared and T squared commute. Okay, so I guess, okay, I'll put a 2 here. Typically, I think when you're looking at a right-angled Artin group, you ignore the labels. But anyways, I put a 2 here. T squared and U squared have kind of no obvious relation coming from the braid relation. So you just conjecture that T squared and U squared satisfy no relation. S squared and U squared, similarly, there's a braid relation there, but there's no relation between S squared and U squared. So this is kind of the, oh, and I probably should have said that this is the conjectured RAG subgroup. And I didn't say it because I forgot, but let me say it now, where RAG just means the labels are all 2. So in other words, you just get commuting relations if your vertices span an edge, and if there's no edge between your vertices, there's just no relation. Okay. Okay, so now there's kind of there's an obvious, oh, I'm gonna go through my sentence here. Let me call that phi. Okay. So there's an obvious homomorphism from the right-angled Artin group on S squared, T squared, U squared into STU, just sending a generator to its square, and Crisp and Paris show that phi is injective. Okay, I'm gonna try to write bigger, I guess. That's not gonna make it neater, but oh well. Okay, so, and they do this for all Artin groups. Okay. And that's in general the right-angled Artin group that you expect. You just keep the 2s, all the labels that are greater than 2, you throw away. Okay, and that right-angled Artin group does inject into the Artin group itself. Let me see. So I'm gonna do a new whiteboard. Are there questions on this one? Now that I just moved it, and I'm not sure I know how to go back, but I think I know how to go back. Oh, view all whiteboards, okay. Is that okay? Okay, so here's kind of the goal, the kind of our original goal with Kasha. Okay. And now we kind of originally thought about it for Artin groups, and now we're exploring it for other groups. So the goal is to find as large, I'll put that in quotations because it's not exactly clear what large means. A right-angled Artin group subgroup as possible. Okay. So, Crisp and Paris had found 1 inside of an Artin group, but we want to find one that I'm going to say is larger, and at least, the very naive thing is that it has more generators, and it turns out to be nicer for a number of reasons. So here's kind of a natural candidate for Artin groups. which again, I'm going to describe just in this example. Okay, so let me redraw the picture. So we have S, T, and U, 2, 3, 3. Okay. And then, well, I'm going to look at S squared, T squared, and U squared. Okay. The S squared and T squared, they commuted originally. They still commute. I'm not going to change. Oops. Switch to right there. Good. I'm not going to change anything there. Okay, so again, sorry. So I guess I'll keep putting 2's here. Okay. Now, so this is the original Chris-Paris rag, and I claim that there is kind of another generator or more generators that are naturally in there. Okay, so if I look at, so this was the braid group on 4 strands. If I look at the subgroup generated by T and U, that's a braid group, a sub-braid group on 3 strands sitting inside the subgroup. And it's a fact about braid groups and in general, what's called spherical Artin groups, that these have centers, which are infinite cyclic. Okay, so there's this, which maybe I'll call delta TU. I guess I'll square everything just to keep it consistent. Okay, well, I do have to square it in this case. So there's a center here of the subgroup generated by T and U, and it commutes, therefore, with T squared, and it commutes with U squared. Okay. Similarly, there's a center on the braid group on 3 strands corresponding to S and U. So I'll put that here. And it commutes with S squared and U squared. I mean, I know that these commuting relations occur. Okay. And of course, there's no kind of maybe obvious relation between that and the center for SU and T squared. So that's why there's no edge between those. So, okay, yeah, I'm already regretting. Okay, these are all labeled 2. Apologies. They all commute. This is a right-angled Artin group, all labeled by 2. And in fact, the whole braid group has a center, which maybe, okay, I guess I'll call that again. Okay. And so this commutes with everything. So, okay, but just, so I end up kind of with this, what I call a fairly natural rag, which is the cone on a pentagon, which is, it's not known to be injective, but at least there's this natural homomorphism, which again, I'll call phi into the, in this case, the braid group on 4 strands. Okay. So kind of this is the conjectured larger rag. I don't know if people can hear my cat meowing, but I certainly can. Okay. Okay, so maybe I'll kind of, so let me draw kind of the braid group picture, and then I'll say the general conjecture that we were interested in. So if you want to imagine the kind of picture where the braid group is the mapping class group of a punctured disk, then the original, and just on 4 strands, the original Crisp-Paris theorem was about the Dane twists along these curves. Okay. And Crisp and Paris show that they generate, well, you can work out what they generate. It's a free product of Z and Z squared, okay, inside of the Artin group. And what the things that we're adding on, okay, I'm gonna, okay, let me just put this in. So these centers of the sub-braid groups correspond to that Dane twist going around the first 3, a Dane twist going around the last 3, and finally a Dane twist going on around all four of those are the center of the whole, or center squared of the whole braid group on 4 strands. Okay, so the kind of the small Dane twists are what Chris and Paris do, and we conjecture that this works in general. So the conjecture, which is still kind of basically open, and I'll write it in kind of full generality. So one thing is we're not allowed to go to squares anymore. We have to say high powers of centers of irreducible spherical Artin groups. So this, if you know these words, great. If you don't, you can just, so a spherical Artin group has the corresponding Coxeter group being finite. If you want to just think about the braid group, this is already a non-trivial statement, where you're looking at kind of exactly these sub-braid groups generated by subsets of the standard generators. So high powers of centers of irreducible spherical Artin groups generate a right-angled Artin group. Okay, so we call this like the generalized Titz conjecture. And it's known, I mean, it's essentially completely open. We do know it for braid groups. This is basically follows from a theorem of Coberta. We don't know it for all of the spherical Artin groups, but we know it for some. We know it for 2-dimensional Artin groups if they have cohomological dimension 2. Okay, but past that, it's kind of a complete mystery. Okay, and kind of the question that maybe motivated us, maybe, well, I'll say it later, but now that we're kind of looking at the Artin groups, and we want to ask this question about other groups, and in particular, ask about graph braid groups. Okay, let's see. Are there questions at this point? I'm going to go to a new whiteboard again.
Kevin, could I ask a question? Are
Yeah.
all the k-pi ones corresponding to this finite?
Mm-hmm. Wait, sorry, say it again.
So what's the cohomological dimension of these types?
Well, we don't know. But so this is the kind of, let me try to go back to the view all whiteboards, go back to this one. So for a general Artin group, there's a natural candidate for a k-pi 1, and its dimension is, you basically look at the largest Coxeter group. So it's the dimension of the largest spherical sub-Artin group. So you look at like the kind of the largest finite Coxeter group that you see in there, and I think add 1. But in general, we don't even know if these groups are torsion-free. So like there's just a big kind of unknown thing about general Artin groups. So we don't know if they admit finite k-pi 1s.
Okay,
but
thanks.
This is kind of the biggest question about them, is what's called k-pi 1 conjecture.
Ah, okay, thank you.
And so for the ones that we, can say anything about, probably not coincidentally, all the things that we say about, they're either the spherical or the 2-dimensional, and these are kind of cases where we do know the k-pi 1 conjecture. So I can say the cohomological dimension of all the examples that we know. Is that okay? Okay, so let me maybe justify or give kind of so why find a large RAG subgroup? I'm going to give a very, again, this is my motivation, so it's a very biased question. Okay, or I mean, I get this question isn't biased, but my answer will be. Okay, so there's a number of reasons why you might be interested in this, and I haven't really again said what large is. I can say that later if you want. Okay, so my reason is, well, I mean, one kind of basic reason is that invariance of RAGs, which I'm thinking about usually kind of a cohomological flavor. That's kind of typically the invariance that that I'm interested in are so these invariants are easier to compute. Okay, it doesn't mean that they're kind of easy to compute, but most of the time, some cohomological invariants are kind of impossible to compute for arbitrary groups, but for RAGs, you can actually do it. Okay, and then sometimes if you know something about a RAG subgroup and you can compute this invariant, you can induct it up to the whole group and say something. Okay, so I'm going to give kind of a very biased invariant or question that I'm interested in. Okay, and I'm essentially asking this because I think it's an interesting question for graph braid groups, and maybe people who are in this crowd who like graph braid groups can tell me that the answer is known, or tell me that it's interesting, or tell me it's boring. Either way, I'm happy in all cases. Okay, so this is kind of an invariant that I've been interested in. So given a group G, okay, it's going to seem kind of like a strange invariant, but let me just write it down. So this is the question: what is the minimal dimension of a spherical manifold? Probably don't have to define a spherical, but I will in a second. So it's just saying that the universal cover in this case is contractible, no higher homotopy groups. What is the minimal dimension of a spherical manifold with fundamental group equaling G? Okay. Okay, so what you can think of this invariant, well, if I replace the word manifold with CW complex, this would be just the geometric dimension of the group. So it's kind of, essentially or closely related to cohomological dimension of the group. And this is saying essentially, what's the cohomological dimension of your group if you're only, forced to live in the world of manifolds? Okay, what has to happen to these invariants? Okay, so with Avermidi, Davis, and Oken, we gave kind of, okay, well, I could say we gave essentially a complete answer. For right-angled Artin groups. Okay. And this invariant, so we can't solve it in every case. We don't know kind of a RAG that where we don't, it's too hard for us to figure out a right-angled Artin group where we don't know the answer. Okay. And this invariant is monotonic. Okay. Kind of obviously, if you have it. Oh, and I should say, just for, if you want to think about this, when there's no assumption on the aspherical manifold at all, it's certainly not closed. That's kind of the not interesting cases. When it's a closed manifold, you can imagine it's not, it has boundary or it's non-compact. Just kind of anything is fair game. Okay. And this invariant is monotonic. Okay, so right-angled Artin group subgroups lead to lower bounds. Okay, obviously. Okay, and this was used to compute like this invariant for some Artin groups. Once you knew for the right-angled Artin group, you pushed the right-angled Artin group subgroup in, and then you could say something about Artin groups. Yeah, and maybe I'll just, okay, I'll say it again. I'm only mentioning this because I do think it's, well, I think it's interesting for graph braid groups.
Oh, Kevin, a question.
Yes.
When you say that this invariant is monotonic, this is not restricted to the case of a right angle Artin groups.
No, yeah, this is just saying that the invariant's usually called the action dimension, which is why I didn't want to give the name, because it's just a kind of not the greatest name. But so this, if it's for a subgroup, then the ambient group is larger than the subgroup.
Yeah. Okay.
That's all, and that's a general fact. Yeah, just look at a cover.
Yeah, thank you.
Okay, so I think it's interesting for graph braid groups. Maybe I'll just again mention some cases where it's two cases where it's known. So for free groups, the answer is 2. Okay. So this is the number, so it's realized by a surface with boundary if you wish. Okay, maybe with some more genus. Okay, and you know it, and so this is an example where this kind of, it depends on the manifold versus the complex. Geometric dimension is 1, but when you want to make it a manifold, you have to thicken it up and you get 2. Okay. And for the braid groups, the answer ends up being 2n minus 3, which you can kind of see in a number of ways. Okay, kind of from the poly-free structure, looking at some action on some type moduli space. Okay, let me see. Okay, so now what I want to do next is kind of describe what we were thinking about, our attempts at proving this kind of computing this invariant for graph braid groups, and then what it led to as an application in topological complexity. Okay, so let me give new whiteboard.
Can I ask a question?
Yeah, of course.
Is there a cohomological lower bound for this action dimension?
Yeah, so it does kind of share similar. Let me go back. So I think it shares some kind of bounds. Okay, maybe I'll put it here. So this number, let's just say, is always obviously less than or equal to the cohomological dimension, but it's also bounded above by I guess twice the geometric dimension. There's some funny stuff at dimension 2 where I guess off the top of my head, I don't know. But maybe I'll just put geometric dimension here for both.
But I guess I was asking if there's a stronger bound in the CD because you're using manifolds.
Well, so in general, no, because I can always look at let me see what. So if I look at, say, like a closed surface, then the cohomological dimension is the same as this dimension. Is that what?
But I mean, for the braid groups, the action dimension is bigger than, well, almost twice as big as the GD.
Right. Right.
And you see that using cohomology, I guess, is what I.
Oh, I see. So
if you've got the CW complex, can't you just embed it in a Euclidean space and then take a regular neighborhood?
Absolutely. And that's one way to get upper bounds. But you have to embed a CW complex into Euclidean space, and usually you only have general position to do that. So that's actually where this upper bound comes from, is you embed. Now, general position would tell you it's actually 2 geometric dimension plus 1, and then it's a theorem of Stallings that kind of up to homotopy, you can change your space so that it embeds into 2n rather than 2n plus 1. Is that okay? And yeah. For the braid group, for this cohomological obstruction, the only obstruction, yeah, so in general, it's very hard to find lower bounds for this invariant. That maybe I should put Besvina, Kapovich, and Kleiner since they computed it here. This is Besvina, Kapovich, Kleiner. They gave kind of the one lower bound, which is kind of vaguely cohomological, but it's a coarse cohomology type of argument. They don't work on the space downstairs. They kind of obstruct the action on universal cover. So they kind of use methods from geometric group theory.
Okay.
So yeah, I mean, this is kind of detected by some cohomology, but it's not clear what cohomology you're using, at least to me.
Thank you.
Yep.
Well, another general question. And you said
yeah.
This invariant, manifold type invariant. In the case of right angle Artin groups, is essentially, you gave essentially a complete answer.
Yeah, essentially.
The answer?
Oh, okay. Good. Thank you. That's like, let me just, sorry, go back here. So let me not give the full answer. This is what you look at, because I have to define some stuff. So for RAGs, so they're defined by graphs. Actually, what I prefer you to think of is that they're defined by flag simplicial complexes. So you just fill in the cliques with simplices. And the main obstruction is kind of top dimensional. So the answer is kind of often it's twice the geometric dimension. Okay. And so, or again, and this is the answer that we gave. And I probably lied by saying essentially complete. That's just from my very biased point of view. Okay, so this is if the flag completion of the defining graph has non-trivial top homology with Z mod 2 coefficients. Okay, so for something like a cycle, this case was known before us. But if I take the right-angled Artin group based off of this cycle, then what this is saying is that the action dimension is 4, not 3. And if I don't have a cycle, if I look at something like this, then this invariant is 3. It's a 3-manifold group. Is that okay? And in general, yeah. So you're looking at, like, if I take like a kind of a crazy rag on a flag triangulation of RP2, I know that it's as high as possible.
Great, thank you.
Yep. Okay, so graph braid groups. Okay, which I'm kind of, I think people here know much more than me. Okay, so let me just write some stuff down for my benefit. Okay, so gamma is now again going to be a graph. We're going to be interested in, so this is endpoint unordered configuration space. Okay. And I don't think I'll ever use I'll probably draw a tilde if I ever need the ordered case, though I don't think I'll ever say it. Okay. And kind of the basic question that we're interested in. So actually, well, you could ask the invariant that we've just been talking about for a while, but I'll give kind of the one that connects more to what we were doing. What is the largest natural RAG, right-angled Artin group subgroup of the graph braid group, this pi1 of the configuration space? Okay. So we want some kind of model on Tit's conjecture. Okay, you have what should be the generators, and where should the right-angled Artin group live? Okay, and I'll give probably kind of the obvious answer, or what our hopeful answer. So in general, we just don't have any idea. I'll give one case which I'm guessing people here have seen many times. I don't know. Okay, I'll call that D, I guess. Okay, so if I have a tripod in my graph, then I can look at, I'll call that T. Then we know that the fundamental group of the 2-point configuration space of T is isomorphic to Z. Okay, so I'll draw the picture. This configuration space always deformation retracts down to a cube complex, and I always just draw the cube complex. Okay, so this is where vertices of this cube complex correspond to pairs of vertices. Let's see, A, B, oh gosh, I'm gonna mess this up. A, D, B, D, BD is supposed to go here. This is just, you know, I guess I just wanted to embarrass myself by drawing the labels. Could have just said it was a hexagon. Okay. So vertices of this cube complex correspond to pairs of disjoint vertices. Edges are an edge and a disjoint vertex. BC. Okay, so I get a copy of Z, and again, we're going around this configuration space. This loop corresponds to kind of an analog, or what I think of as an analog of a Dane twist. Okay, moving, you know, two robots or 2 points around this tripod. Okay, so that's kind of what I would hope would be a natural standard generator. Maybe I'll mention another one which was useful. So if you look at more points, then you get now a free non-abelian group, I think on 3 generators. Okay. And the other one, which I guess, okay, I should put here is if you start having degree bigger than or equal to 3, okay, then you only need 2 points. Again, this configuration space deformation retracts to a graph, and now the graph, so this is again free non-abelian. Okay. So at least if we're trying to get, again, I'm not sure whether you should look at squares. I don't know whether you should look at high powers. Again, high powers are kind of harmless in the sense that the RAG subgroup doesn't change. But I'll say it, so it turns out that this subgroup, oh, sorry, so it turns out, not that this subgroup, that's skipping ahead. Okay, so what do we get from this for a graph braid group? So for large n, so for a large number of points, we get a free group. I'll just say F2. You can always look at a subgroup. So you get some product of free groups, some direct product of free groups into your group, where this is now the number of essential vertices. So for me, an essential vertex is just degree bigger than 2, I guess, of gamma. Okay. So, and you can, you can guess the right number of points. So if I have a degree 3 vertex over here, I'm always assuming that everything is very subdivided. So they're kind of far away in my cubical configuration space. Then I put 3 points kind of locally over here, 2 points locally over here. I get a free group here and a free group here, and they end up commuting. So I get, a direct product of 2 free groups. And in general, this is just kind of the local thing that you're given by looking at a graph braid group. You get a free group at every point, every essential vertex, if you're willing to put a large number of points. Okay. So I guess large means, 2 times degree bigger than or equal to 3 plus 3 times degree 3. Okay. And then it turns out, okay, so this is kind of, I mean, as long as you're willing to choose huge points, this right-angled Artin group subgroup is basically as big as I want in my biased viewpoint. So maybe I'll say, so it turns out, I think the existence of this subgroup isn't surprising to anyone. I think only to us, because we didn't really know anything. So it turns out that this subgroup, what hopefully was somewhat surprising, is that this subgroup gives lower bounds to topological complexity. again, that maybe that's not surprising to people who know about it, but that's what we used. Okay. And I should say, so of course, this is kind of, we were very motivated by, or kind of, we had been thinking about this problem and then started reading these papers of Ben Knudsen. So he had given the same lower bounds on topological complexity, which I guess I'm going to call TC, right? That's what I should call it. I was going to say, I'm not going to give the definition of topological complexity because, I mean, everyone here knows more than me, and you can just blame Dan for not talking to me enough about topological complexity. That's why all his fault.
Dan, you're a bad guy.
What's
Dan,
that?
I said, Dan, you're a bad guy.
Okay, gave lower bounds on topological complexity. He gave the same lower bounds with an additional assumption on having no, so this graph having no non-separating trivalent vertices. Okay, so something like a suspension of 3 points is an example where we kind of know the topological complexity now, and before it wasn't known. Okay, but I mean, he basically, we essentially followed his proof and then had some tricks at the end. Okay, so the main theorem that we use to give, and again, this was kind of one of his main tools as well, or okay, was this theorem of Grant, Lupton, and Oprea. So if you have two subgroups, again, this is kind of at least for us, this helped us give a lower bound on topological complexity without knowing too much about what it is. Okay. So if H0 and H1 have disjoint conjugates, okay, where this means that if I look at G, H0, G inverse intersect H1, this is always 1 for all G. Okay. Then the topological complexity of the group is greater than or equal to the cohomological dimension of the direct product. Okay. And of course, this is interesting because this cohomological dimension of this direct product is often, or should be oftentimes larger than the cohomological dimension of the group. There's no reason that this H0 times H1 is a subgroup. Okay. So in particular for us, we're looking at like a direct product of free groups sitting inside our graph braid group. And so there's kind of two natural subgroups, which I think are the same ones that Ben uses when he was looking at his work on Farber's conjecture, and then the ordered case as well. So there's kind of two z to the n subgroups where you just take elements in each of the F2s. That gives you two zns, and hopefully they have no disjoint conjugates. And then you can apply this theorem, and then that gives you the topological complexity is, well, in this case, is a twice the cohomological dimension of the group, so it's kind of as large as possible. Okay. And so, well, the kind of the new tool that we use, so let me just say this, what we involved was this kind of tricks from geometric group theory, okay? So Kasha is really a geometric group theorist. And people in geometric group theory, this is kind of one of their bread and butter things. They want to control kind of how they look at kind of some interesting subgroups of a geometrically interesting group. They want to understand how the conjugates of them intersect. Okay, so there's a lot of tools. We kind of got away without using any heavy machinery and just some tricks, but that's basically just because I prefer tricks. Okay, let us control conjugates of these two subgroups inside of F2 to the n, or inside of the graph braid group. Okay, so there's a lot of tools that are developed. In this special case, we had tricks, but I mean, it'd be not interesting, I think, to see whether, or maybe people have, whether, or the tools that people have used in geometric group theory can be applied to topological complexity. Okay, so let me tell you kind of, okay, so I don't know how long it usually goes, Dan. Does it go for an hour or?
50 minutes usually.
Okay, let me tell you.
You can go over.
Well, okay, we'll see. Okay, so let me give you kind of, yeah, the first trick, which is a construction of Crisp and Beast. I'll just give it very briefly, I guess. Okay. So as I said, this configuration space is homotopy equivalent to a non-positively curved cube complex, where the n cubes or the k cubes correspond to, you know, tuples of k disjoint edges and n minus k disjoint vertices. There's also, this is also true for any rag. So any rag, A gamma is as well. I shouldn't say A gamma, let me just say ag is as well. Okay, in this case, it's this non-positively curved cube complex is for the rag. So this is the natural model for the k pi 1 of a rag. It's sitting inside, so this is a subcomplex of some large torus. Okay, and subtori correspond to simplices in the nerve, so they correspond to cliques in the graph. Nope, I shouldn't call it gamma again. Okay, defining graph. Okay, so you make a huge torus, and then you put in turns out you put in all the one skeleton that corresponds to the vertices of your defining graph. Then you put in two-dimensional subtori corresponding to the edges, and then you keep going, filling it up with three tori if you kind of see the boundary of them in there. Okay, and so Crisp and Beast define a local isometry from this kind of cubical version, which I'll just call the cubical configuration space of the graph braid group, into this natural Salvetti complex of some k pi 1. Okay, so for some rag. Okay, and it's the fact that local isometries in this non-positively curved world induce pi 1 injections. So you get this injection of the graph braid group into this right-angled Artin group. Okay. So this is, let me just again say the kind of the morals here. So the first thing is that in this world, local isometries are easy to construct. Everything is non-positively curved and very combinatorial. We're just working with non-positively curved cube complexes. So there's kind of a link condition that you just have to satisfy, which tells you when you get this local isometry. So these things are not necessarily too hard to construct. And kind of the main feature of these right-angled Artin groups is that rags are very flexible. Okay, so because you can define them using any defining graph, and you automate, so this graph can be kind of whatever it wants to be, and you get this very nice non-positive curvature and combinatorial structure. Okay, so in particular, given this, so they basically just make this ad hoc obstruction given a graph, gamma, Crisp and Beast, make a new graph. So now I'll give it a name called delta of gamma. I'm sure this has a name in the graph theory literature. I just didn't look it up. Okay, so they make this new graph. And so let me say here, the vertices of here of the new graph correspond to edges in gamma, and the edges in gamma correspond to disjointness. You can imagine they're essentially just cooking up this new graph here so that it's going to emit a map from the configurations, the endpoint configuration space of your graph into the Salvetti complex, or this kind of subtorus for the RAG. Okay, so in particular, let me just, the map that they construct is, so maybe, sorry, I'll draw a little over, but let me just draw a couple pictures. So for example, if I look at this star graph that I've been interested in, for the local picture, this crisp beast, so this is gamma. This is just 4 points, if I did that correctly. On the other hand, at some point, you do have to, even for like a tripod, if you're looking at more points on the configuration space, like 3 points, you need to subdivide the tripod so that it's homotopy equivalent to this cube complex. And you can check, you end up with some kind of more interesting graph. And in general, you get kind of this huge graph. Okay. So you're looking at, this is, again, gamma, and then this is the delta of gamma, okay, which you can check. Okay. And what this is saying is that the graph braid group here should inject into the RAG here. Okay. And if you think about it, just if you see in gamma, if you see some disjoint edges and disjoint vertices, something that should correspond to a cube in your endpoint configuration space, or the cubical model, then because you have disjoint edges here, in delta of gamma, you get a 3 simplex, or 2 simplex. This gives you a 3 torus in that kind of combinatorial, or in the non-positively curved k-pi1 that you've constructed. And so that, they've just done it in such a way so that the 3 cube in the configuration space can map into the 3 torus. And you check that it's a local isometry, and it's not too hard an argument. Okay. Okay, so very quickly, let me just kind of say why would you want to do this? Okay. So we want to control, again, to apply this theorem of Grant, Lupton, and Oprea, you want to control conjugates of these subgroups inside of a graph braid group. So it turns out to be easier. It sounds harder, I guess, but for us, it's easier to control conjugates inside a right-angled Artin group instead of the graph braid group. Because the graph braid group, I guess we don't quite understand well enough. And for RAGs, we have a little more control. And in particular, but of course, since this is bigger, if you can have subgroups with disjoint conjugates, and you can show they have disjoint conjugates inside some big group, then you definitely get it for the small group. Okay. So again, this is bigger, but it's also kind of more controlled. So one of the nice features of RAGs is that they retract onto any subgroup, or onto any kind of special subgroup, which I haven't defined. That just means corresponding to an induced subgraph. Okay. So if you have this large graph and you look at an induced subgraph, you get a retraction of the thing down to whatever you're interested in. And what that means in our context is that so for one thing, retractions play nicely with having disjoint conjugates. So if you're kind of have disjoint conjugates in some small group and the big group retracts onto it, then you have disjoint conjugates in the big group. Okay. So it suffices to understand kind of conjugates in a local picture. Okay, where I think this is probably very believable now. So I have kind of maybe some pictures like this in my graph. again, some essential vertices here, which I'm imagining I've subdivided all this so that kind of they're kind of, I can only concentrate on the local thing. Okay. If I look at the crisp Vist rag and I look at just the subgraph corresponding to the edges around every one of the essential vertices, this gives me, so I get kind of a product, of crisp Vist rags for the local picture. Okay. So we first want to control conjugates in here, then it suffices to control conjugates in here, this much smaller right-angled Artin subgroup. We've kind of isolated the problem. This is also a direct product. So really what we now need to do is to control conjugates on each one of these kind of individual pieces. And in that case, you're looking at like, cyclic subgroups of a free group, or possibly if you're looking at, got switched to an eraser, or possibly conjugates inside of a rag based off of this graph. Okay. So there's kind of one more trick maybe for dealing with that case, but it's really, at this point, you're reducing it just to the local thing, and that's it. Okay, and since I have 5 minutes over, I will stop here. Thanks.
Thank you, Kevin. Any questions?
Yes, I have a few ones. Let me just point out one observation about this thing that you said, that this technique of finding the largest possible right-angle Artin group inside graph break groups.
Yeah.
Gives you nonsense lower bounds for the topological complexity of graph break groups. Let me just point out that actually this is very strong because I don't know if you've noticed more or less recent paper of Ben, where he proves that these lower bounds are actually give you the actual TC of these spaces. And this is a preprint in the archive that is going to appear in a soon to be out book that we are preparing. So
okay. No, so I did I know of that this is the Farber's conjecture and beyond. Yes. Right, and yeah, so in this case, though I should say we don't have anything to say about the unordered case. Like we can't use our methods to somehow simplify his argument for Farber's original conjecture. Or did I say unordered? I meant, yeah. The original Farber's conjecture we can't simplify in any way, but the kind of unordered case, this crisp Vist trick did it.
Yeah, you're right. Sorry. The other thing is actually related to the unordered case of graph break groups. This general problem that you posed about finding the largest possible right-angle Artin group inside pure break groups, the order things.
Yeah, okay. Yeah.
It's a very strong problem, and let me just think of this milder version. Just decide which pure break groups are right-angle Artin groups, and this is the original much of the original motivation of Rob Rice about studying the topology of these very interesting spaces. And my comment and question is, well, there is, in the case of the unordered break groups, the complete break groups.
Yeah.
There is a very nice, almost complete characterization of which of these groups are right-angle Artin groups. So I was wondering if, and in the case of order configuration spaces, namely pure break groups, I think this is not much is known about which pure graph break groups are right-angle. So I was wondering if you have thought of that milder problem.
No, so I mean, I think we took a brief look at some of the papers, which were kind of saying which ones were right-angled Artin groups, but I don't think we I don't think I have anything new to say about like, yeah, that's somehow probably harder to say like that this thing is exactly a RAG rather than finding kind of this kind of infinite index big thing. But yeah, that's interesting.
Well, the point is that if you can answer your problem, you would be able to answer the milder problem, because if you say, well, I know that this is the largest possible right-hand Artin group, the question of the milder problem is, well, it is total or it is not.
Oh,
maybe this has to do with the fact that you haven't told us about what it means to the largest possible.
yeah, no, that's true. Right. So yeah, I can say that it essentially, what I think of as large is having interesting homology in the flag complex that you associate to the RAG where you fill in all the cliques of the defining graph. So I think of for me at least, this RAG is bigger than that one. And there's reasons for that. So there's like, so if you look at some kind of cohomological invariance, not cohomological dimension, but kind of, I can just say it, I don't know why so if I'm interested in like what's called the L2 homology of this group, but also the invariant of this thing that I just defined. So this is like a 3-manifold group. And this is not, this is only 4. So I guess this is what I mean by large, is that there's a cycle here and a tree here, and that's what I'm kind of interested in detecting. So this shows you, for example, that this cannot be a subgroup. The RAG on the left can't be a subgroup of the RAG on the right, whereas I think, I'm not positive, but I think I can find this one inside of that one.
Okay.
Yeah.
Thanks.
But yeah, I'll have to think about what you said for hitting it on the nose.
Any further questions? Well, we can continue. I'm going to stop the recording now. Let's thank Kevin again.